Hi there. During this session we're talking about weightlessness and the different ways where you can achieve that feeling. First of all, I will take you through some basics. Okay. If we were in a lift, and you were not accelerating in any way, that would mean that the force you'd be applying to the set of scales you have in the lift is equal to mass times acceleration. So if we look at this as the weight, it means that the weight is going to equal to minus mass times gravity, which equals 0, so the weight equals mg. Everything seems perfectly fine there. If you're standing in a lift, you look down, the weight which will be shown on the scales will be equal to exactly what you expect, mass times g. If we're in an accelerating situation, things change a little bit. If we're accelerating upwards, and you may have experienced this, when you're in a lift and you accelerate upwards, you can feel maybe at the start or at the end, you can feel, especially at the start, you may feel kind of like as if you're getting heavier. The weight increases, and that's actually what's happening. If you're accelerating in the other direction, now what you have to do is incorporate that into your calculation. Now, if you're coincidentally accelerating upwards at a value of g. Now what we have here, if we apply force equals mass times acceleration, we've got to remember that your body is going to be accelerating upwards, and although there's still a mass times of gravity, that force going downwards, what the scales will show is that weight is going to be equal to 2 mg. So think about that through. If you're accelerating upwards at a value of g, that means the weight shown on the scales is going to equal to 2 mg. So if you want to increase your weight, it seems like accelerating upwards is a good way of doing it, but we're talking about weightlessness. So now if we reverse the situation. Now if you're accelerating downwards at g, then you have what's known as weightlessness. And the lift example kind of works well, but this is any situation when you are in free fall. Now the reason for that, and the lift helps it because there's a set of scales that put on the lift, is if we do force equals mass times acceleration. That means that you are accelerating down at accelerating downwards. So that means if we consider the weight is going to be equal to minus mg, and that's going to equal to minus mg. So therefore the weight is 0. Therefore you feel weightless. Now, so we often see this, and this is a situation used to much effect in what was used to be known as the vomit comet, when planes would go up into the higher atmosphere and then dive down to allow you to simulate a weightlessness for brief periods of time. Now, if we think about situations when you're in free fall is also what happens in orbital motion. The reason for that is, as you're in orbital motion and you're in a fixed position, what you find is the change in velocity due to orbital motion is equal to acceleration to the center of that circular system. That means that you're accelerating towards the center of the system, so therefore you're in free fall. This is great because it means that what we have is orbital weightlessness. So, for instance, an astronaut orbiting a spacecraft, and an orbiting spacecraft has a centripetal acceleration equal to g1. So it's a different value of g because we're not on the surface of Earth, but it's a value. And where g1 is the acceleration due to gravity at the height of that orbit. Now at the same time, the spacecraft also has the same centripetal acceleration. So what happens is that both of you are accelerating, and the astronaut therefore has no acceleration relative to the spacecraft, so therefore there's a feeling of weightlessness. Finally, I should round it up. If you're in deep space or you're a long way from all over gravitational attraction, you will also feel weightlessness. So that is my explanations of types of weightlessness. I hope you found it useful.